Okay, good morning, good afternoon, good evening, everyone, wherever you are. My name is Stan Chung, and today I'll be presenting our work on comparing aluminum oxide and hafnium dioxide-based MOSCAP III-V silicon power splitters and de-interleavers for DWDM optical links. So I'd like to thank all my colleagues listed here for their contributions, and also ARPA-E for funding our work. So to start things off, I put together a sort of motivation slide. At HPE, we have announced the commission of several exascale supercomputer systems for various government agencies within the US. And just to name a few, the Aurora system at Argonne National Labs is expected to exceed 2 exaflops by 2022, and El Capitan at Lawrence Livermore National Labs will exceed 2 exaflops by 2023. So we're continually looking at new optical technologies that both integrate electrical to optical interfaces that can deliver higher data transmission with improved power consumption across supercomputers. And so we'll talk about some of the more long-term outlook of these enabling optical technologies. Shown here is what a typical ring-based DWDM architecture might look like. And we have two versions, with one being on the top and the other being on the bottom. So you start off, or you both start off with a spectrally wide comb laser, and you can either de-interleave or power split these comb lines into a spatially separated bank of high-speed microring modulators. The signal is then sent over optical fibers and then into a receiver which consists of various types of photodetectors. Now, on the receiver side, there are issues with polarization diversity, but those are details we won't get into in this talk. So at Hewlett-Packard Labs, we proposed a novel DWDM architecture with a goal of full heterogeneous integration capable of 1 terabit per second data rate and less than 1.5 picojoule per bit energy efficiency, operating up to 50 degrees C. So some of the differentiating concepts are itemized here. We use both DWDM and spatial division multiplexing with a single quantum dot source, and that can be off-chip or on-chip, ideally on-chip, and that's being led by my colleague, Geza Kurtzfeld. We also have non-return to zero medium bandwidth modulation per lambda or wavelength. And we also have integrated III-V silicon with a dielectric in between MOS capacitors. And this enables athermal and efficient channel control for various devices such as lasers, modulators, and de-interleavers. And this also allows for efficient NRZ modulation with ring modulators. My colleague Suda is developing these. We also have co-integration of both germanium and III-V on silicon, and we have multiple flavors of sources and detectors, sources being monolithic and heterogeneous in a combined version, and also silicon germanium detectors and quantum dot avalanche photodetectors down here shown in the cartoon of the receiver demux. So here's the slide summarizing the landscape of the state-of-the-art III-V silicon MOSCAP phase tuners. Now, it does say a complete survey, so I apologize if I've missed anyone's work in the audience. If so, you can let me know in the Q&A section. There has been quite a bit of work in the 1.55 micron wavelength regime, as well as the indium phosphide, InGaAsP, aluminum oxide dielectric MOSCAP structures over the past decade. We've also listed our work in comparison with everyone else's in the bottom two rows. Here we have gallium arsenide with aluminum oxide and also hafnium dioxide. In regards to a figure of merit, such as V pi L, it's not a world record, but as we'll see later, it facilitates the integration of ultra low power components, such as de-interleavers and modulators with quantum dot comb lasers. So from an integration point of view, it's a pretty big deal. So our single mode hybrid MOSCAP structure is shown here on the upper left. The wafer bonded 3-5 region is a moderately doped 150 nanometer thick gallium arsenide layer. So here we have a cross-sectional SEM image of the device, and over here is a TEM, or a transmission electron microscope image of the bonding interface. And so for this particular image, we use a combination of both hafnium dioxide and aluminum oxide, with the main dielectric being the hafnium dioxide. The reason why we put some aluminum oxide on the periphery is because it helps facilitate the wafer bonding. The figure to the left shows the simulated effective index change, and that's on the left axis. And also on the right axis, we have the associated plot for the free carrier absorption losses versus applied MOSCAP voltage. And so this is done for several dielectric thickness of aluminum oxide from 5 to 25 nanometers. The same is done for hafnium dioxide on the right. And so again, to put these values into a V pi L figure of merit from a simulation point of view, if we assume a length of 500 microns, an aluminum oxide thickness of 5 nanometers, we'll have a static V pi L of 0.13 volt centimeter. And for a higher K dielectric, such as hafnium dioxide, thickness of 5 nanometers, we'll have a static V pi L of about 0.09 volt centimeter. So here in this slide, we compare experimental and simulated refractive index changes of our MOSCAP structure. So we've actually fabricated these devices on a platform with 3 different variations, and they're denoted by design 1 through 3. In design 1, we have silicon doping of 4e to the 16 with aluminum oxide thickness of 6 nanometers. In design 2, we have a bit higher silicon doping, except instead of the aluminum oxide, we have 10 nanometers of hafnium dioxide with a small amount of aluminum oxide surrounding it. And then in design 3, we have a thinner hafnium dioxide stack, and the silicon is undoped. And so the graph here on the left shows the changes of various aluminum oxide thickness versus bias, kind of shown in the previous slide, and we compare that to measured results indicated by the purple squares. And so the measurements point to either an effective thickness of 15 nanometers or a different refractive index value. Likewise, for hafnium dioxide, measurements indicate either a larger effective thickness of the stack or a change in refractive indices. So we're currently investigating these issues with TEM imaging and CV measurements. But one can see, even with the hafnium dioxide thickness almost twice as thick as the aluminum oxide thickness in design 1, we get slightly better phase shift. And so we can improve on this by even making the hafnium dioxide thickness smaller than the 10 nanometers for this design 2 case. So this slide shows the various types of MOSCAP de-interleaver architectures we've investigated. They include second order and third order AMZIs, and also 1, 2, 3 ring assisted AMZIs shown in C through E. And we also have cascaded second order ring filters. And each design has advantages and disadvantages in terms of passband flatness, passband roll-off, and insertion loss. And so in this slide, we show some of the results of the de-interleaver. So measurements were taken on a 1 ring assisted AMZI, or 1 Ramsey structure designed for 65 gigahertz spacing. And we show results for different MOSCAP dielectrics as indicated by design 1 and design 2, and they're color coded by their boxes. So, fabrication non-uniformity and directional coupler variation due to edge differences between the 2 wafers play a significant role in determining de-interleaver performance, such as passband, crosstalk, and symmetry. So due to this, it's difficult to make a fair comparison between design 1 and design 2. However, we searched for devices on the 2 wafers that yielded similar crosstalk values before phase error correction. That's shown on these 2 left-hand figures. In any case, the figure on the top row shows the measure optical response with the aluminum oxide, 6 nanometers. And so before phase error correction, the measured bar and cross channel exhibit crosstalk values of minus 7.3 dB and 10.7 dB for the bar and cross channel respectively. So after phase error correction with a bias of minus 2 volts on one of the delay lengths, that results in improving the cross channel crosstalk from 7.3 dB to 16.4 dB, and the bar channel crosstalk from 10.7 to about 27 dB. So at applied voltage of minus 2 volts, approximately 5 nanoamps was drawn. So that results in a total tuning power of 10 nanowatts. So the bottom row shows results for the ring-assisted AMZI with the hafnium dioxide dielectric with a thickness of 10 nanometers. So by applying a minus 2.1 volt bias on the ring, the cross and bar channel crosstalk improved from 13.8 to 16.4 and 6.8 to 13.7 dB respectively. At this bias of minus 2.1 volts, about 24 nanoamps was drawn, and that's a total tuning power consumption of 50 nanowatts, so significantly better compared to thermal tuning counterpart. You can note that the passbands are far from the flat top compared to theoretical designs. So this is attributed to waveguide losses, whereas increased channel crosstalk indicates non-ideal power coupling. So in the future, this can be remedied with robust 50% MMI power couplers and also improved fabrication to reduce waveguide losses. So in summary, we've demonstrated a comparison between aluminum oxide and hafnium dioxide MOSCAP devices, and we've showed some results for MZIs and one ring-assisted AMZI interleavers. We've shown DPIL values of 0.37 and 0.94 volt centimeter for the aluminum oxide and hafnium dioxide-based MOSCAP structures. And then we've shown crosstalk improvement down to minus 27 dB with only 10 nanowatts of power consumption. And not only are these useful for DWDM optical links in terms of power consumption, but they can potentially be used for future large-scale low-power neural networks and programmable photonics. Okay, that's it. Thanks.